This is the next video in the chapter on stoichiometry of chemical reactions. We just learned what the word stoichiometry means and how to use it to convert between reactants and products and products and reactants and products. But we did so in the context of pancake making, and we need to talk about it in the context of chemical reactions. So stoichiometry in a chemical setting, when you make that stoichiometric ratio in chemistry, it will probably look something more like this. It will look more like 2 moles of carbon monoxide over 1 mole of H2. It usually involve moles because moles is the way chemists like to measure things. But you may remember that there is no such thing as a moleometer. You cannot just put something on a balance and measure the number of moles. That's the number that we have to calculate based on measuring something else. So we need to take that into consideration in our plan for doing these types of problems. So we use these stoichiometric ratios to convert between compounds. But before we can do that, there's something we need to do first. So before we can use the ratios, we need to convert to moles. Converting to moles is a pretty awesome, guaranteed successful first step whenever you don't know what to do in a chemistry problem. So that is going to be your new go-to first step. So if we had moles of some compound, likely one of your reactants, one task you will frequently need to do is convert to moles of something else, usually one of the products. This is just like converting from number of pancakes to number of eggs. We're going to use that stoichiometric ratio. And we're going to abbreviate it because that word is hella long. So this is the step we know how to do using that stoichiometric ratio. We just need to add some preliminary steps to get to the number of moles first and to get from number of moles at the end to the unit that we actually want. So we can start with different kinds of units that we measure. Sometimes we measure the volume of a particular compound. Sometimes we measure the volume of a solution if you have a solution of the compound you're interested in. Sometimes we measure the number of things if we're counting number of molecules or number of atoms or number of formula units. And sometimes we can measure the mass. So we need a way to get from each of these units to the number of moles. And these are all things that we've done before. So if we need to get from number of things to number of moles, we have used Avogadro's number in the past. 6.022 times 10 to the 23rd things per 1 mole. If we need to convert from the volume of a solution of something to the number of moles of the solute, we can use the molarity. That's a tool we've recently learned how to use. If we want to convert from volume, we need to go through mass first. So our handy dandy tool to get from volume to mass is density, usually in grams per milliliter. And then from mass, we can convert to moles using the molar mass, either of one element or of a compound. So there may be an extra step or two needed to get from the number you are measuring yourself to the number of moles of something. Once you have the number of moles, you can convert to moles of the other thing you're interested in. And then once you have moles of the other thing, you can do these same conversions again for the other compound. Just remember that the second compound you've converted to probably has a different molar mass, it probably has a different density, and it probably has a different molarity. So we are not simply inserting the same number on the beginning and the end, or we wouldn't bother to do it. The densities are different, the molar masses are different. This is just a process. So we can use this diagram as a guide as we do a couple of actual chemistry examples here written at the bottom of the page. So go ahead and take a second and write these down, and then we'll start the problem. So this first one says, how many moles of ammonia are produced when 2.41 times 10 to the 24th formula units of calcium hydroxide are used up? So let's look at the roadmap here. We are starting with calcium hydroxide. That's going to be our compound A. And we are trying to find out information about ammonia, which is going to be our compound B. We want to find moles of ammonia, so this is where we're going to stop. And we have number of things of calcium hydroxide, so this is where we'll start. So we're going to have two steps of dimensional analysis. One step to get from number of things to number of moles of calcium hydroxide, and one step to get from number of moles of calcium hydroxide to number of moles of ammonia. So let's go ahead and set that up now that we have a plan. So we'll start with number of more formula units of calcium hydroxide. So our first step is to go from number of things to number of moles using Avogadro's number. So I want to have moles on the top, because that's the unit that I need to use in the next step. And we'll put number of things on the bottom. 6.022 times 10 to the 23rd formula units of calcium hydroxide. Okay, so now we need to do the moles step, and that's our stoichiometric step. So we need to have the balanced equation, and I see coefficients are included here, so this one is already balanced. So I want to get rid of calcium hydroxide, and I want to end up with ammonia. So I go looking for those in my balanced reaction. Here's ammonia, there's a 2 in front of that one. And here's calcium hydroxide, there's a 1 in front of that one. Oh, I forgot moles. 2 moles and 1 mole of each of those. So those cancel, and now I have moles of ammonia, and that's the unit that I'm looking for. So we plug that into the calculator machine, and we should get 8.00 moles of NH3 produced. There we are. So no matter what we need to do, if we're converting from one compound to another, we're always going to need this stoichiometric ratio mole to mole step. There just may or may not be some pre and post steps that we need to do. So this one only had pre steps, and then this was our core stoichiometric step here. So let's do the next one, because the next one is going to involve some pre steps and some post steps. So the next question says, what mass of carbon monoxide is required to react with 25.13 grams of iron 3 oxide? And here's the balanced reaction listed below. So I can see that I've been given a mass of something, iron oxide. That's going to be my compound A. And I'm looking for the mass of something else, carbon monoxide. That's going to be my compound B. So to get from that start to the finish, I'm going to need one step converting from mass to moles. I'm going to need a second step converting from moles of one thing to moles of another, and a third step converting from moles of that second thing to the final mass. So I'm expecting to have 3 steps in my dimensional analysis. So we're starting with what we know, and we know that we have 25.13 grams of iron 3 oxide. So my first step, convert mass to moles using the molar mass. And I don't know what the molar mass of iron is because I haven't calculated it yet, but I'm on a roll here, so we're just going to leave a space for it and keep going. So I'm going to put moles on the top and grams on the bottom. So grams cancels, and I'm going to leave a circle, and I'm going to come back and fill it once I'm done setting up. So now I need to go from moles of iron 3 oxide to moles of carbon monoxide. That's going to be my stoichiometric step. So I want the iron oxide to cancel. I want the moles of carbon monoxide to still be there. I check my balanced reaction. There was a 3 in front of carbon monoxide. There is a 1 in front of iron oxide. So moles of iron oxide cancels. Then we need our third step, going from moles to mass. And I'm going to use molar mass for that, but I'm not just going to use the molar mass from before, remember, because this is the molar mass from iron oxide. I need the molar mass for carbon monoxide. Totally different compound, totally different molar mass. Still don't know what it is, so I'll just put a circle and I'll come back. All right, so now I've got grams of carbon monoxide. That is the answer to the question I wanted. Okay, this is my stoichiometric ratio step. That is the all-important middle step of the process. Okay, so molar mass, we're going to calculate that by looking at a periodic table. I have done that. So now I figured out that it's 159.6884 grams of iron oxide per mole. And the molar mass for CO, carbon plus oxygen, 28.0097 grams per mole. Sometimes it's just easier to get the problem solving process with the unit set up first and to come back and do those little side quests at a later time. Okay, so now we have all the numbers we need. We're ready to calculate the mass of carbon monoxide. And if we put those numbers in the calculator machine, we should get 13.22 grams of carbon dioxide needed. Ta-da. And notice that in this first example we did, we were going from a reactant to a product. And in the second reaction, we were going from a reactant to another reactant. So we can use those stoichiometric ratios to convert between any two things that are in the reaction, no matter where they are located. So now that we are experts in using stoichiometric ratio, we are in the next video going to talk about how to figure out which one of your reactants is your limiting reagent.